This is the 20th lecture. So, because there seems to be a lot of fatigue, I decided not to assign homework 8, and I'm not going to do the last two lectures next week. So, the last material for the final exam will be the lecture on Friday. So this is the second last lecture. Um, yeah, so in this lecture, we're going to discuss a result that summarizes pretty much all the most important information that we've learned in the course about elementary probability. So, this is what's called the central limit theorem. So, we had the de Moivre-Laplace theorem, which told us how to use the normal distribution to approximate the long-term behavior of coin flipping games. And we had the weak law of large numbers, which told us some fact that deviation from the mean in a sample average becomes increasingly unlikely with time. And so both of those results are fundamentally based on this construction of a sequence of independent, identically distributed random variables. So, in the case of the de Moivre-Laplace theorem, what we assumed is that we have these random variables which are representing the score in the coin flipping game, and because the coins are fair, the score in one round has no effect on the score in any other round. And so the hypothesis of independence is the idea that the coin is fair, and the hypothesis of identical distribution tells you that you're using the same coin every time, not only in the sense that it has the same bias, but in that you're repeatedly observing a coin flip rather than changing to observing a die or some kind of other probabilistic experiment. So the coin flip game is the simplest example of a sequence of independent, identically distributed random variables. And we were able to get really good information out of the de Moivre-Laplace theorem, whereby we could predict the probability that the long-term result of the game is going to be within any specific interval around the mean, where you measure the interval in standard deviations. And so the weak law of large numbers doesn't give you as much information. It just tells you that the sample average is going to converge to the mean, but it doesn't allow you to do detailed estimates of the probability for various intervals around the mean, whether they're getting smaller or not. You can use the de Moivre-Laplace theorem to estimate a lot of different probabilities, whereas the weak law of large numbers doesn't give you a single piece of numerical information outside of the general assertion that the sample average is going to converge to the mean. So we would like to have a way of bringing these concepts together and getting the kind of detailed information we had with the de Moivre-Laplace theorem in the same generality as the weak law of large numbers, because if you remember, the construction for the weak law of large numbers just was any sequence of independent, identically distributed random variables. Whereas the construction for the de Moivre-Laplace theorem was specific to the coin flipping game, where you have a binary random variable. And so we thought of the de Moivre-Laplace theorem in the context of a competitive game where one player's score is subtracted from the other player's score to get the result of the game. But you can modify the de Moivre-Laplace theorem to deal with any two outcome random variable. So any kind of sequence of independent, identically distributed random variables with only two outcomes can be thought of in the context of the de Moivre-Laplace theorem. But the general construction of a sequence of independent, identically distributed random variables is much broader and allows you to account for any possible number of outcomes as well as a random variable that's changing continuously. So the statement of the central limit theorem you can see highlighted in teal at the bottom of the page is designed to resemble the statement of the de Moivre-Laplace theorem, and we'll see a more detailed presentation of that reduction in a subsequent page. But you can see that what's being calculated here is the probability that a sum of independent, identically distributed random variables lies in an interval around n mu. So we have the idea that mu is the common mean, and we're adding up n of these things, so we get n mu for the mean of the sum. And then we have the idea that sigma is the common standard deviation, and when you add up n independent random variables, the standard deviation scales like the square root. So square root n sigma is the standard deviation of the long-term sum. And what we can see is that this is measuring an interval around n mu in units of square root n sigma. And that's the fundamental idea that we had with the de Moivre-Laplace theorem, which we're now seeing holds in a much more general context, where you have an arbitrary sequence of independent, identically distributed random variables. And we get that this probability is again approximated by the probability of the standard normal lying within the bounds that you're using to measure the interval for the long-term result. So we have a lower bound of A, and that means we put a lower bound of n mu plus square root n a sigma, because we're supposed to be thinking of n mu as the center, and square root n sigma as the unit. And then we're scaling in terms of a. And on the upper bound, we have b, and we're centering at n mu and scaling in terms of square root n sigma to get this upper bound of b. And we can calculate it the same way we're used to with the de Moivre-Laplace theorem as 1/2 ERF b over root 2 minus ERF a over root 2. Okay, so the central limit theorem is widely understood as the reason for the ubiquitous emergence of bell curves in large-scale statistical patterns. And so there are many practical consequences of this mathematical phenomenon. And probably the most important is the idea that you can estimate a much larger population from a small sample if you use the small sample to figure out the mean and standard deviation. And once you've done that, it's often thought of as reasonable or even necessary in empirical science to assume that the large population is distributed like the central limit theorem predicts, with the mean and standard deviation that you figured out from the small samples. So the sample allows you to approximate the mean and standard deviation of what's understood as an underlying phenomenon. And then you can use the normal approximation to assume that things are going to be shaped like a bell curve with that mean and standard deviation. And making that assumption tremendously simplifies all parts of statistical analysis and things that depend on data analysis, because it allows you to avoid having to really deal with mathematical details about what the random variable might do on a small scale. You're just making the assumption that on a large scale, what I'm going to see is a bell curve, and all I really need to figure out is the mean and standard deviation to understand everything I need to know about the distribution of the data, because the large-scale distribution in the whole population is just going to be a bell curve with an appropriately scaled mean and standard deviation, where I can get really detailed information about error probabilities and using the central limit theorem. And obviously the justification for this is the kind of microscopic to macroscopic transition that is the main topic of statistical physics. But if you're interested in the applications of statistics rather than how to derive statistical phenomena from underlying physical principles, you can just take it as pretty much given that macroscopic phenomena in the world are modeled as a sum of a huge number of tiny contributions from independent, identically distributed factors. So the temperature average on a given day can be calculated as something that you measure in a relatively small scale on the scale of one day, and then you can look at, well, you measure the temperature average as something that you record over the course of one day, but you understand that it's being influenced by a huge number of tiny contributions from other phenomena that happened on other days or are happened earlier in the day or were ongoing throughout the day. And so you're measuring a certain thing, which is the temperature, and you understand that there's a gigantic number of things which are affecting this, but they're all having effects which are pretty much sampled from the same underlying distribution, and moreover, the effects are not correlated with each other. And so we have the fundamental model of statistics where a macroscopic phenomenon is being produced by contributions from a huge number of independent factors, which are all being sampled by the same random law and which are not strongly correlated with each other. And, the extent to which things are correlated with each other is usually perceived as structure, and things that follow the laws of probability are perceived as randomness. But there's an extremely powerful emergence of structure in the large-scale limit of randomness, where if you have no correlations on the factors coming together to produce your phenomenon, then you can be guaranteed to see a bell curve. And so the central limit theorem gives you a prediction for the probability of the long-term average being within a certain error interval around the mean. But in a broader sense, it can be thought of as kind of enforcing a geometry of data, whereby if you have a lot of numbers that are produced by sums of independent random processes, when you visualize this, pretty much any reasonable visualization will look like a normal distribution or a higher dimensional normal distribution. And, graphs are the first way of dealing with data in a geometric way that can really be extended to all kinds of linear algebra and calculus, where the unifying theme is the picture rather than the technical details, but it's the picture of the bell curve and its higher dimensional variance, which appears again and again. Okay. So we can see how to make a comparison between the central limit theorem and the two sort of predecessor results that we've discussed earlier. So the central limit theorem is this sequence of independent, identically distributed random variables where the common expectation is mu and the common variance is sigma squared. And you can just specify the common variance by specifying the variance of x1. And you can specify the common mean by specifying the mean of x1. And then the central limit theorem is telling us that we have this approximation for the probability that the long-term sum is within a certain interval around the mean by the probability that the standard normal is within the same interval. And so the de Moivre-Laplace theorem, we had these coin flips with a bias of p towards heads. And we had these explicit parameters where we always had specific values of n and p. And when we were dealing with the de Moivre-Laplace theorem, what we kept doing was calculating 2p minus 1 for the mean and 2 square root p1 minus p for the standard deviation. And then we had to multiply the mean by the number of trials and the standard deviation by the square root of the number of trials. And once we did that, we were able to approximate these error probabilities by the standard normal. And so what we can see with the relationship between the de Moivre-Laplace theorem and the central limit theorem is that you just have a special case where these are binary random variables. And if you have a binary random variable, the expectation and variance both depend on this parameter p, and we can calculate the expectation was 2p minus 1 and the standard deviation was 2 square root p1 minus p. We did that when we first introduced the coin flipping game. And so now that we have this reduction, we can see that the de Moivre-Laplace theorem really is a special case of the central limit theorem where you're dealing with binary random variables. Okay. And we can also have a look at how the weak law of large numbers is a consequence of the central limit theorem. And what the idea is in terms of deducing the weak law of large numbers from the central limit theorem is that a violation of the weak law of large numbers has to scale linearly with the number of trials, or else it's going to get crushed when you take the sample average. And so if you want to think of the weak law of large numbers in terms of the sum rather than the average, what you see is that any positive error in the average turns into an error that scales linearly with the sum. And the central limit theorem tells you that there's a gigantic probability that the error is going to be smaller than the square root, or something that scales like the square root. And so eventually what's going to happen is this linear error is going to look like a huge multiple of the standard deviation, and so the central limit theorem will tell you that it's extremely improbable. And we can see how that works out if we try and do the change of variables to go from a positive error in the average to the errors estimated by the central limit theorem. So we start with the probability that n mu minus n epsilon is less than the sum, and the sum is less than n mu plus n epsilon. And we got those bounds by transferring the normalizing division by n in the average to a multiplication on the bounds. And the weak law of large numbers tells us that the probability of the average being within any positive error interval around the mean converges to 1. And so we can see that the weak law of large numbers can also be thought of as saying that the probability the error is sublinear converges to 1, no matter how slow the linear rate of growth in the error you're inquiring about is. So once we do the change of variables to go from a linear error to an error that scales like the square root of the standard deviation, or scales like the square root of the number of trials with a rate that's equal to the standard deviation, then you can see that you have this compensating factor, which is square root n epsilon over sigma. And so what that's telling you is that a linear error, when measured in the appropriate units, actually looks like a probability that the standard normal is within an interval that expands to infinity. So because you need to put this square root n in the bounds of the interval to shift from a linear error to a square root n error, that ends up telling you that the probability of having this linear error is the probability that the standard normal is within an interval that has width square root n. And so as n goes to infinity, that interval expands to cover the whole line, and the probability converges to 1. So there is a little bit of subtlety in terms of using the central limit theorem for values of a and b that are changing instead of being fixed. And in this deduction of the weak law of large numbers, we omitted some technical discussion of why that's justified in this context. But in general, in order to use the central limit theorem confidently, you should have fixed parameters a and b. Okay, so we can see this example of how we can use the central limit theorem to recapitulate the same form of calculation that we were using for the de Moivre-Laplace theorem. So you probably have a sense that these calculations we were doing with the de Moivre-Laplace theorem are by far the most detailed calculations that we were doing in this course. And we're improving that detailed method to a much broader context here. But the basic form of the calculation is the same. So we have 9,000 copies of a random variable with expectation 5 and variance 2. So when we have this independent, identically distributed copies, we know that we can apply the central limit theorem. And so we're asked to estimate the probability that the sum of these 9,000 independent, identically distributed random variables is less than or equal to 45,100. Okay, so we can see that what we need to do is to first of all determine the large scale parameters from the small scale parameters. So we have this idea of n mu, which is the long-term expectation, and that's just 9,000 times 5, which gives us 45,000. And then we need to have the square root of 9,000 times the square root of 2, which comes out to 60 root 5. Okay, and so then we can figure out how to rewrite the bound we're asking about in the correct way, which is as a deviation from the mean scaled in units of sigma. And so, or scaled in units of square root n sigma. So we have n mu is 45,000 and square root n sigma is 60 root 5. And we need to multiply the 60 root 5 by a factor which gives us addition of 100. So that tells us we need to multiply by 5 over 3 root 5. And so when we rewrite things using the central limit theorem, we can see that we're asking about the probability that x1 up to x 9,000 add to at most 45,100 is the probability that x1 up to x 9,000 add to at most mu plus sigma 5 over 3 root 5. And so we convert that using the central limit theorem into the probability that the standard normal is less than or equal to 5 root 3 over 5, which comes out to be roughly 0.952. Okay, so we can see here we're asked to estimate the probability that the sum of 2,000 rolls of a fair die is less than 6,800. And so you can see that the central limit theorem is this kind of cheat code for gambling games that have no human component, because it lets you figure out virtually anything you want about a mathematical gambling game over the long term. And so you can see why when this was discovered, it really changed the approach people had to games of chance from kind of psychological narratives about divine intervention into calculations that give you numerical answers. And so we have in lecture 9, where we first introduced expectation and variance, one of the first calculations we did was to see the expectation and variance of a fair die. So we can see the expectation of a fair die is 7 over 2. And the standard deviation is root 105 over 6. So we can ask where the mean of the long-term sum is going to be 2,000 times 7 over 2, which gives us 7,000. And we can see the standard deviation of the long-term sum is going to be 105 over 6 times the square root of 2,000, which comes out to be 50 root 21 over 3. So we can do our adjustment where we rewrite the bound that's being inquired about in terms of the previous calculated mean and standard deviation, and we get that the necessary compensating factor to give us 6,800 as a deviation from 7,000 in units of 50 root 21 over 3 is 12 over root 21. So the central limit theorem is going to imply that this probability is approximated by the probability that the standard normal is less than or equal to minus 12 over root 21. It's a pretty small probability. It's about 0.00441. So you can see how it's not at all intuitively obvious that scoring 6,800 from 2,000 rolls of a fair die is such an unlikely thing. I mean, if you're thinking of a fair die as something that comes out to be roughly 3 or 4, well, 6,800 is not that bad approximation to 2,000 times roughly 3 or 4. And even if you know that it's supposed to be exactly 7,000, it's pretty hard to figure out that this deviation of 200 from a 7,000 mean already crushes the probability down to 0.00441. So, the central limit theorem can not only give you detailed information at a single level of probabilistic order of magnitude, it can also tell you that something is actually like several orders of magnitude smaller than you might guess with an intuitive heuristic. Okay. So this last example is kind of about the limitations on what you can expect from the central limit theorem. So we want to consider a sequence of what would be called standardized, identically distributed random variables. So to standardize a random variable means to subtract a constant so that the mean is 0, and then to divide by a constant so that the variance is 1. And if the mean is 0 and the variance is 1, subtracting by the mean and dividing by the variance are both trivial operations. So a random variable with mean 0 and variance 1 is a result of a standardization operation, and a further standardization has no effect on a random variable that's already been standardized. But what we want to think about is the case of identically distributed random variables where the average converges to 0 exponentially fast. So this is like a really, really strong kind of convergence to the mean, where the sample average is going to the 0 with a quantitative rate of exponential decay. And what we want to see is that these random variables cannot be independent. So the central limit theorem gives you not only positive information about convergence to the mean, it also gives you negative information about the impossibility of exponentially fast convergence to the mean in a sequence of IID random variables. So we can see how to think about that mathematically, where we're saying, okay, we have this idea that with approximate certainty, the sample average converges to 1 exponentially fast. So we're going to translate that into mathematical language by saying there's some positive number c, which is the rate of exponential convergence, such that the probability the sample average satisfies our rate of decay converges to 1. So the sample average is decaying exponentially, with probability that converges to 1. And so we can try and understand why that's inconsistent with independence of the random variables. And the reason it's inconsistent with independence of the random variables is because the central limit theorem tells you that you actually will have errors that are roughly as large as the square root of n. And an error as large as the square root of n causes more than an exponential deviation from the mean in the average. So the central limit theorem tells you that independent random variables, you will have some noise which prevents the average from converging to the mean exponentially fast. And so if you have exponentially fast convergence to the mean, then there has to be some sort of correlation between the random variables, which is making that happen. So the basic example of what you could think about in terms of this situation would be if you have a coin which is rigged to come up opposite sides every time you flip it, then the score in the coin flipping game is going to be ridiculously small compared to any parameter that grows with the number of trials. Because if the coin is completely rigged to alternate sides, you'll have the player that flips first scores 1, and then the opponent subtracts it back to 0. Then the player who flipped first scores 1 again, then the opponent subtracts back to 0. And the score will just alternate between 1 and 0 forever with this weird rigged coin that alternates sides. And because you have this rigged coin, the long-term sum is not even growing at all. It's not growing linearly like the average. It's not scaling like the standard deviation. It's going to look tiny compared to both the average and the standard deviation as soon as you have n is large, because if n is large, then 1 and 0 look really small. So the central limit theorem says that you can't have something so dramatic happen in a truly random situation. If the sample average is looking so close to the mean that it's converging exponentially fast or even just not growing at all, then the way you can think about that is to say that the sample average is coming from some sort of rigged process, and it's not actually a random phenomenon, because the central limit theorem predicts that you really will have errors which are as large as square root of n. Because the probability that mean zero sum is bigger than the square root of n is roughly the probability that the standard normal is bigger than 1. And the probability that the standard normal is bigger than 1 is not 0. Whereas if the sample average were being decayed exponentially fast, then the probability of a square root n deviation would be crushed by the complement probability of exponential adherence, which would go to 0. So you can't have exponential adherence with independent random variables because the central limit theorem would say that the probability of a square root n error is too high for that to be realistic. And exponential convergence here is kind of extreme overkill. You can see that anything faster than 1 over square root n convergence is not likely to happen in the average. So even asking for linear convergence to the mean in the average is not something that can happen for independent random variables.